Yeah, what we're going to do in the next few lectures, as I mentioned last time, is what this micro, meso, macro modeling in a good amount of detail. Going from particle dynamics, like following individual particles, to following probability distributions, to following moments of the probability distribution, right? So that's the micro, macro, meso, the micro, meso, macro chain. And we're going to be looking at three systems to go through this transition. And the first one you've already seen, at least in some sense. And then we go to the two hard spheres colliding, which we will take this problem, we'll cast it as a in terms of the first problem. And then from 2 we go to n. And when you get n to infinity, then we have the classical Boltzmann equation, right? So that's what we're going to do. And the reason why we're doing this, of course, the Boltzmann equation is very useful, and we're going to see some very interesting applications of this. But even more so, let me write it down explicitly why we're doing this, other than, of course, there is useful things there. So first of all, micro, meso, macro modeling is relevant in so many problems, right? So that topic itself is interesting. But we also will learn about phase space. I mean, some of you have seen phase space in various scenarios, maybe in terms of dynamical systems, it's very easy to visualize, but high dimensional phase spaces is one. But also, how do you take a problem that is very high dimensional and try to reduce dimensionality in phase space? I think that is something that we will learn. We'll also learn about the Liouville equation, which we'll get to very, very quickly, as early as this lecture. And typically people see Liouville equation in a very particular context, unless you're taking a math class where it's more general. And so we'll be somewhere in the middle, right? So funnily enough, like any ordinary differential, I don't know how many of you know this fact. Any ordinary differential equation, okay, let's assume certain level of smoothness and things like that. You can take any ordinary differential equation, nonlinear ordinary differential equation, and you can write it as a linear partial differential equation. How many of you knew this? Okay. Very few. And this is an amazing fact, right? So think of any complicated, however arbitrary complex it is, with some smoothness, ODE, and you can write it as a linear PDE. And why would we want to do that? Of course, it sounds like you're transforming a nonlinear problem to a linear problem. That's interesting, but the linear problem will be in very high dimensions, okay, as many dimensions as there are unknowns in the ordinary differential equation, right? But because it's linear, it lets us do some operations, because when things are linear, there's a lot of machinery that's available to you that you can use to your benefit. And we apply those machineries in linear space, and then we can come back to the nonlinear space. And for those who have taken gas dynamics or a CFD class, this is kind of, you can think of the linear PDE as the PDE, and the characteristic equations for that PDE as the some straightforward connections there. And then of course, Boltzmann equation is very important. We'll get a little more insight into entropy by the end of this lecture. So far, I've introduced entropy as some kind of abstract quantity related to information and bits, but in the physics context, we'll get more insight. We'll also learn about collision integrals, the Boltzmann equation, and it's very important because a lot of the modeling that we do in real life goes into physical modeling. is in the collision equation, in the collision integrals. We'll also learn natural coordinates. Right, so you have physical coordinates like position and velocity and things like that. But sometimes to solve a problem, if you can identify natural coordinates, then you can be much more efficient and you can make approximations much more natural. And then change of variables. In a probabilistic sense. Right, let's say you have a probability distribution of y, but then you have some other variable x, and x and y are related. How do you express probability in terms of x? It's a simple formula, but when you're applying in context, I think you'll get a lot more insight. We'll also learn about statistical equilibrium. Like for instance, what is the final, at long times, what is the distribution going to be? And many times, even though the problem we are modeling is very difficult, time evolution is very hard, using, say, a maximum entropy principle or something like that, you can get many times an analytical distribution for the equilibrium. Okay, and that's very important. Even if you're doing non-equilibrium physics, you think of it as deviations from equilibrium and you can build models. Again, this entire class is about predictive modeling, right? Various concepts. So the idea of statistical equilibrium and modeling departures from statistical equilibrium can get you really far. And I want to put this out there, okay? So when you go long chain derivations, okay? So when you go from, I said you can cast 2 in terms of 1, and then use that to come back to 2. We're going to be doing a sequence of steps, maybe 10, 11, 12, I don't know how many ever steps there are. And that is a skill I also want you to like learn or master. Especially, I was thinking about it, especially in the age of AI, when you can go to Claude or GPT and you type something, it can give you that next step really well, okay? And sometimes it is, I mean, I'll admit, sometimes even for things I know, sometimes it's better than me. Of course, if I ask the right question, it can give me the next step to a really remarkable degree of accuracy, especially the latest models that are out there the last couple of months. And the reason I say that is, what is the role of the human and human intelligence in this age of AI, where very quickly, and in many cases they're already there, it can give you very intelligent responses and next steps. Humans, I mean, can have some kind of lateral intuition, and models, at least now, and I don't think this is going to change in the next year at least, they can't do very, very long chain things, right? They can, if you ask the right question, they can give the right answer, or a pretty reasonable right answer. But you know, to think of a problem, to configure it in your brain, you've to figure out a bunch of steps, and then knowing how to go from one step to the next, right? Maybe the how to go from one step to the next, the AI model can help. But AI models cannot do this long chain derivation. What I'm showing you, like this, even this thing, AI models cannot do right now, absolutely not. But even in this derivation, in a couple of places where I either got stuck or I needed a calculation, I would go and ask Claude or GPT Pro, and that helped me. But the long chain derivation it cannot do. And I want you to like be able to like handle in your mind, load a long derivation, and maybe the individual steps and the sophisticated details is something you can offload. But I think you can change derivation. Okay, so that, well, I think that's pretty much all of the things. Well, and there are a few other things also. The concept of ergodicity. So we're going to be pretty much learning all of these things in this in this basically one set of examples. And conventionally, maybe if I taught the class a couple of years ago, I would have introduced each of those as separate concepts and given you very simple examples that correspond to each of those and maybe connect to a bigger example. But here I've kind of flipped the script. We have a problem, and in the process of solving the problem, we'll kind of go through all of them. Okay, so that's the idea. Any quick question? Okay, so that's the setup. Now let's get to modeling. Okay, first we start with, let's call it the circular scatterer. And the setup, as we know, as we've seen in the past, is the same. You have a square domain of length L, it is periodic, and then you have the circular disk of radius sigma, and then you have particles with some velocity that collide with that circular object perfectly elastically. Okay. So now let me just say, so in this particular case, again, you have the particle has some initial velocity. That magnitude does not change, right, even after collision, but the direction changes. And again, if theta is the, let's make it simpler. Okay, so let's say this is the sphere, and then or the circle, and you have a particle with velocity v, velocity magnitude v. And this angle theta, right? So theta is basically represent the direction of the velocity component at a particular time. And then you have, and then of course, this is going to basically collide with this disk at this point. So at that particular point, there is going to be, okay, maybe I shouldn't have drawn it like this. Let me draw something that's a little more instructive. Just because I don't want both angles to be the same. Draw something like this. Okay, so that's better. So here is where the particle is going to hit. Now, at that particular point, there is, wherever the collision happens, you're going to have a unit normal. And n is represented in terms of phi rate. cosine phi I plus sine phi j. Okay. So theta is the angle of the velocity vector of the particle, and phi is the angle of the normal at the collision point. Okay. So in this scenario, you can write, so let's call the pre-collision velocity as v minus. Okay. Just Newton's laws is going to give you v plus to be v minus minus 2 v minus dot n. Okay, so this is directly from Newton's laws, right? So nothing. Maybe in high school you didn't do in vector form, but it's the same thing, right? Just expressing what you know, but in vector form. There's another way of writing this, which is even more useful. So theta out, or so before collision, your particle had an angle theta. After collision, let's call that theta in. After collision, the angle is going to change to theta out, and that's, again, just using geometry and specular reflections, you can write it in this form. Okay. So these are both equivalent. You know, this is in vector form, and this is in this angle form. I think angle form is better because we're going to be using the angle as one of the phase space variables, and this becomes more convenient. Okay. So again, just Newton's laws of specular reflection written in angle form and vector form, and these are precisely the kind of things you can ask GPT to derive it quickly. Because when I did it first time by hand, I forgot that pi, and I actually wrote a code, and it didn't work. So then I forgot that there's going to be a pi just because of geometry. Any quick questions here? Okay, so far just Newtonian mechanics, right? Nothing is complicated. All right, so now let's do Meso modeling. I'm going to define a transport equation. I'm going to define F. This is a probability density, and this is the quantity for which I want to find a transport equation. Okay, so what does F mean? Can someone tell me in your words what F means? What does F mean physically? Yeah.
The likelihood that a particle takes a state characterized by V and RV.
Yeah, correct, right, and yeah, precisely. So there are two ways of thinking about this, and I would prefer the second one, right? But let's talk about the first one. In the first case, you assume there are a large number of particles, okay, and they're scattered all over space. And so this F would tell you, if you basically take a particular portion of, so for instance, F delta R delta V, where delta R is a small area around this R, and delta V is a small area around V. So you can say, one way of interpreting is, so this gives you the total fraction of the particles that are in that particular region of phase space. So you basically said, position and velocity are my phase space variables. So this gives you fraction of particles R in R plus or minus delta R over 2 V plus or minus delta V over 2, right? You're taking, so you have 4-dimensional space, and in that 4-dimensional volume, you have particles distributed everywhere, like all of you submitted in your homework, right? Precisely that. You have a large number of particles, and then you're asking, okay, in this particular part of phase space, how many particles there are? So this is one interpretation, and this is more like, for people who know what I'm talking about, it's more like a mean field assumption. Okay? So the better assumption is what? What's your name?
George.
George. What George said is the better assumption. So, or the better interpretation. So interpretation 2 is there's only one particle, okay, but we don't know where that particle is, and we don't know what its velocity is. Okay? So then it is likelihood of finding that particle in, well, let me call this as some region A, right, in region A. I mean, these two are equivalent in some sense, but in this class, we mostly work with this, because in this scenario, the way to think about the problem is there are many possible realizations of where that particle is and what its velocity is, and but there's only one particle, and so basically this represents the probability density function of finding that one particle in that particular region of phase space. Okay, and so, but the example you did in homework 1, this is perfectly consistent with both views. Okay, in this case, you're assuming you fill your space with so many particles. So what is the fraction of the particles in that space? Here, what you've really done in the process of doing that homework problem is you've instantiated many realizations. So you basically superimpose many realizations of that problem on one plot. So each of those are basically the same particle, but different realizations of them. Okay, so this is better. And, yeah.
If we have a time interval for a time interval?
Well, this is at that particular time.
So if we had a time interval?
Yeah, you can do time interval too.
But the meso like kind of regime needs in the sense that that time interval is bigger than the time of the actual events are happening, no? Because if not, this wouldn't be probabilistic.
Yes, but now we have Newtonian dynamics, so there is no issue with time and time intervals and anything. If you're thinking more time becomes discrete, there is all those other processes you got to worry about, yeah, then it's relevant. But here, our phase space is R and V, and we're evolving F over time on that phase space. So there is, again, it's a very good point, right? When we start with physics, when you're trying to model a gas, or when you're trying to do plasma or all of that, which is when mostly people in engineering and science see these things, then you're a slave to all of those assumptions. Here, everything I say is 100% precise. There's nothing else required. This is it. Mm. And let's build towards that plasma and whatever from this, but not making many arbitrary, I don't want to make continuum assumptions, quantum mechanics, nothing. This is like a precise universe. And this is a vehicle to like traverse that universe better. Okay? When Boltzmann, I think Boltzmann, when he wrote the equation, he probably took that interpretation. Okay, any questions? Okay, so that's the F, okay? That is what we are trying to write a transport equation for. And so Well, you've seen the notes, so I don't need to go through everything that is in the notes. So how do we, first of all, so this is a 4-dimensional phase space, but we can immediately, for the given problem setup, we can reduce it to a 3-dimensional phase space, right? Because, you know, you can write velocity as magnitude times cos theta and sine theta, but this magnitude is a constant before after reflection. It's all in this particular problem setting, it's always constant. So effectively, I'm going to go from a phase space of RV to a phase space of just R theta. So you've gone from 4 to 3, okay? And in many problems, that itself is enormous reduction of complexity. Imagine, for instance, going from 3D to 2D, right? You can imagine how much complexity is saved, and similarly going from describing something from 4 to 3 is you know, huge savings. So now let's derive a transport equation for f of r theta t. Okay. So I'm going to consider some region of phase space. So this is basically position vector. This is again where is that particle? Okay. So this is let me draw the entire phase space. So phase space is 3-dimensional. So the phase space in R is, you know what it is, right? Basically a square with the center cut out, and then you have theta. And of course, theta goes from 0 to 2 pi, and theta is also periodic. So one of the examples you set up in homework 1, if you were to represent that example in phase space, remember you started, you initialized the whole thing with velocity of 0, right? With the angle of 0, right? Everything was pointing in the horizontal direction. In that case, if you want to like if you wanted to represent f over phase space for that example, how would it look like? Sorry?
Delta function.
Yeah, so it would be obviously it would be all over this plane, but it would be a delta function in theta, right? Because the theta angles are all 0 to start with. And then what happens after a while? How would the PDF look like? Yeah, it starts spreading out, and at infinite time, what do you expect? Yeah. So at infinite time, f of, actually you can write f of r theta infinity would be very easy to write, right? So in this dimension it will be 1 over 2 pi, and in this direction it will be 1 over area, right? So this will be 1 over 2 pi times 1 over L squared minus pi sigma squared, right? So this would be the PDF at f of r theta infinity. And in fact, for that particular initialization, f of r theta 0 would be 1 over L squared minus pi sigma squared times delta of 0. Okay, so this is the, for that particular initialization, this is where you were.
But there's a fixed portion of particles that will never collide. Right? I mean, that large distribution will never diffuse.
Actually, you're correct. You're right. So, yes, you're right. I jumped ahead of.
You have a measure zero set. That's a.
Yeah, exactly. No, I was immediately thinking about. I was thinking about the second problem where, because of collisions between particles, in the end everything will go to that equilibrium. But right. So let's not do that. But we will understand that there is. Well, this is correct. Thank you for pointing out. So this is the initial, and then there's going to be some level of diffusion, but the diffusion won't be. It won't be a uniform distribution, because some particles, only because there is no collisions. First of all, there's only one particle, right? Everything is just a realization of the same particle. So that part, some realizations will never collide. Okay, so that's basically the setup. And if you see in the notes, which you would have seen, so here is an example. Right, so here is an example. So this is the PDF of, say, the initial location, it's the initial PDF, initial marginal PDF, and then things spread out. And if you solve the Boltzmann equation, which we'll derive for this particular case, this is how it is. Then there are particle collisions, and then you have all of these. But yes, there is a measure zero set always, because there's only one particle. Some realizations never collide. Okay.
But even for the n particle case, there will be some particles that will not collide. Just because you have no collision, so is everything elastic?
Everything is elastic, but infinite time, that every particle will collide. Infinite time.
I don't know, if you convert to the Gaussian, there has to be some events that will not hit the zero.
Oh, they will absolutely hit zero. Absolutely hit zero. That's what I was telling in the previous. If you have two particles, right, and one particle is moving like this, the other particle is moving like this, and if at collision, if this is the particle velocity and this is the particle velocity, this will slow down to zero. Mm-hmm. So at infinite time, every particle will collide. But anyway, that's more of a final point. But anyway, these are the kind of things we're after, right? So this is, if we're able to get, basically you have this blob as initial condition, you want to derive an equation for how that blob evolves, okay? So, if you write, so now assume some part of phase space. I don't know. I'll just say there is some part of phase space. Some volume in phase space. I'll call it, I don't know, some kind of curly V or something. So that's some volume. And if you do time derivative of f of r v, sorry, not v, you're in data space. So I'm just taking some chunk of phase space, then this is just inflow versus outflow, right? If you think of it as a fraction of particles, it's pretty much mass conservation. If you think about that particular volume, there are no sources or sinks inside that particular volume. So whatever number of particles come in have to go out, or whatever number of trajectories or realizations they have to go out. So this would just be minus, I'm just doing mass conservation, nothing sophisticated. I'll just say S nu, so these are the F times V dot theta dot N nu. Okay, so all I've done is done mass conservation, right? If you go to interpretation number 1, this tells you that the fraction of the particle, the rate of change of the particle fraction or the number density, whatever it is, in that volume is basically governed by inflow minus outflow, right? It's just your continuity equation. There's only one slight complexity, right, which is in your, so what is the mistake that I did here? My second mistake of the day so far.
Should not be taught. We describe.
Sorry?
We described the respect to theta already.
Yeah, so first of all, what I should have written there is R. Right, so this is, so when you typically write mass conservation for when you learn fluid mechanics or something, we would write something like d by dt of your rho dv is minus integral rho v dot n ds, right? So this is your mass conservation. I've done exactly the same thing, except here, where does this velocity come from? It is derivative of position. It's derivative of one of the base space variables, which is position, right? So that is exactly what I've done. So this is the, I mean, I could write it as we call this as velocity, right? The same thing. But this is more fundamental, right? So if you're evolving this over some set of variables, then the flux is the whatever you're modeling times the rate of change of that particular coordinate, right? That's the right interpretation. So R dot and theta dot, because R and theta are our coordinates. Any questions? Is there anything that's not clear? So, yeah.
The second equation is R a vector? The position.
Yes, thank you. And this n is a normal in the 3D space. Is that a question? All right, so now if we know R dot and theta dot, then we're fine. So let's now consider a case where you're away from the collision boundary. Okay, so I've chosen that volume to be not lying this. Okay, so what are the equations of motion? What is R dot away from the collision object? Sorry? Right? R dot equal to V, right? Change of rate of change of position is velocity. So what is theta dot? Sorry? Why is it 0?
We can have velocity vector in terms of theta, and since the velocity is not changing.
Yeah, right. Away from a collision, remember this box is away from this circle, right? So away from that circle, theta cannot change. Theta can only change once there is a once there is a collision or right at that moment of collision. So basically now you have d by dt of integral f of r theta t is dv is minus integral f times v dot n ds. Okay. And so we're going to do the same thing we've always done, right? You can write, so, and I want to call this as, I don't know, for some reason I've written it as u here. Oh, no, it's fine, the notes is fine. So then I can apply divergence theorem to it, right? As we've always done, and then I can apply it to all volumes. So you get the end d by dt of f plus b of theta dot gradient of r f equal to 0. Okay, so this is what I get. So this is the transport equation. This is how the probability density evolves as long as there is no collision. Okay, and there is no collision everywhere in the domain. Right, there is only a collision on this circle here. Okay. So outside of that circle, this equation is perfectly valid. But on that circle, we have a very simple relationship. So f of sigma, right? Sigma, so this is r greater than sigma. Okay. Whenever r is greater than sigma, this equation is perfectly valid. But when r equal to sigma, f of sigma theta t is going to be f of sigma two phi plus pi minus theta comma t. Okay, so this equation is valid for r equal to sigma. And of course, then in the periodic boundaries, you have periodic boundary conditions. I don't want to write it, it's trivial. Okay, any questions? So that's it. Now you have the equation and you have the boundary conditions, right? So it's done. So this is an example of a mesoscale model where, I mean, for our particular problem setup, we did not have to make any assumptions, right? The problem setup itself had assumption that you have one particle, collisions are elastic, and periodic boundary conditions, right? That's it. That's the problem statement. For that particular problem statement, to get to this mesoscale model, we did not have to make any assumptions, okay? But for many other, for more complex problems, going from micro to meso will require you to make some approximations. Approximation is the word I was looking for. So we did not make any approximations in getting to this equation. Okay. Starting from the micro model, we did not make any approximations. And that's a rare case. But in many cases, we will have to make some approximations. Okay, any questions, challenges to this? So, if you look at the notes, chapter 2, you can see this derivation. And so what is shown here is I'm actually solving the equation that we just derived, right? So I've actually done both. So here, this is my microdynamics, right? I'm taking many realizations of the particle, right? This is my initial realization, and then I'm simulating Newton's laws directly, right? Like you did in your homework one, right? You've already kind of done this. Of course, my initial condition is in space is just a so-called wrapped Gaussian. Okay, look it up. Difference between a Gaussian and a wrapped Gaussian, you look it up. And then I can evolve this, so that's the micro. But this is the meso. So here I have solved the equations that we just derived, only because I couldn't help myself over the break. I have to solve PDEs, so I solved that PDE. Okay, so this is how the PDE solution is. Not very sophisticated. So remember this equation. So this equation, what would you call this equation as in your CFD or numerical methods? Sorry? What?
Non-conservative.
Yeah, this is just a linear this is the linear advection equation.
Yeah.
But linear advection with what? Linear advection equation with non-constant coefficients. But in each theta plane, you solve a constant coefficient linear advection equation. But in different theta planes, your velocity is changing, right? Cosine theta. So I want you to start thinking now in 3 dimensions, where the third dimension is theta. Okay, and I also want you to think of that boundary condition, right? How is that boundary condition going to be implemented in your code? It's actually very interesting. I would ask you to think about it, right? So this is the part of the phase space that's on the sphere, right? So you have some theta and some r, so a whole bunch of particles may enter here, and then they may leave. The same amount of particles would basically leave out of, actually this is wrong. They would actually leave from here, because they'll have to leave from the same r, right? So this is your, say, theta in, and this is your theta out, okay? So a bunch of particles are going to leave the domain at one point and re-enter the domain at another point, and that flux is conserved. Okay? So I want you to, again, you're used to thinking in terms of space and time. Now I want you to think about space and theta. Okay. Any questions here? I mean, if you want, so the next thing we will do after this flipped class homework is I'll ask you to choose any problem you want that's related to what we're doing here, and I would want you to solve it. Maybe some of you will choose to solve this Boltzmann equation using whatever method or whatever. Okay. Any questions? Okay, good. So we've derived our first mesoscale equation, and we did not have to do any modeling to go from any modeling approximations to go from micro to meso. The only modeling we did is look at the equation and say phase space does not need to be 4-dimensional. Phase space can only be 3-dimensional, right? So that's the only modeling we did, but that did not involve any approximations. And by the way, this equation is called the free streaming or the collisionless Boltzmann equation. Okay. And again,
For the collision equation, you will just have a term in the right-hand side, no?
yeah. In fact, I did that too. I didn't upload it because it's a little complex. Whatever I wrote as the boundary condition, can actually be written as a collision integral, even for this problem. And then you have everything there as one equation, not an equation plus boundary condition.
And then I guess this makes it more interpretable.
Yes, because you come from Ricardo's group. You like that word. Anyway, all right. So here is me solving. So here, the blue line is the particle method. Pretty much what you implemented in homework 1 is the blue line. But of course, in homework 1, actually this is exactly what we did in homework 1 almost. So here all the particles are initially have an angle of 45 degrees. Okay, initially in one of the homework problems, initially your particles all had 0 degrees, right? So I'm just looking at the marginal probability, right? That's the other thing I want you to think about. So F is distributed over R and theta. Now I'm integrating F over R. So I have the marginal distribution in theta. Okay? So the marginal distribution initially is a delta function at 45 degrees. And then after a little while, again, for now just follow this blue line. It turns out it peaks at 225. Why is it peaking at 225? Yeah, reflection, right? So remember, so this is your circle, and a whole bunch of particles were initialized at this location, and they all had 45-degree angle. So when they hit, the initial collisions will be distributed like that, and this is 225 degrees, right? And then, yeah, some other things happen, some interesting things happen. So the red dashed line is me just spending a couple of hours to solve that Boltzmann equation. With some more time, I can implement a better method with limiters and high order and whatever, and get closer to the solution. But at least it's a crude solution. You can do better if you spend a little more time. Okay. Any questions here? Okay. All right. So now, again, the reason why I wanted you to read the notes is because, of course, you can follow what I'm teaching, and also I can spend less time on a whole bunch of algebraic manipulations. Okay. So now let's talk about entropy. So remember, F is a probability density function, right? And when we define entropy earlier, we define it as minus pi log pi, right? So this is how we defined Shannon entropy earlier. We can use exactly the same logic, or almost exactly the same logic, and we can define an entropy, and typically this is called Gibbs entropy, Shannon-Gibbs entropy, and some people just call it entropy. It doesn't matter because it's the same structure, right? Here you had a discrete PDF. Here you had a probability distribution function, and here you have probability density function. But logic, everything just carries over, all the same. And I call that H here. And now I can do some manipulations, and I can, just like I derived a transport equation for F, I can also derive a transport equation for H. Just because I already have a transport equation for F, I'm just going to plug it in here. Okay? So that's how these things come out. So if you do a few algebraic manipulations, actually extremely straightforward, but just being careful, then you can show this. This is why I wanted you to read the notes, and then if you have any questions, you can ask. The entropy does not change in time. Okay, so this is called the fine-grained entropy. there is a difference between this and the Boltzmann entropy, which is what we are more used to seeing in this context. And those differences are very important. But the key takeaway is for this particular problem, the fine-grained entropy does not change. So why does it not change? What's your explanation? So it looks like initially things were very concentrated, and later things all spread out. That seems like entropy should have increased, right? Because initially you, or at least some level, your first order thinking would be entropy could have increased, but why did it not increase? Yeah.
You have all the information from the initial condition anyway, so there's no information there.
Exactly. Yeah. So the initial condition has a certain level of uncertainty, and then all of these equations, the underlying equations that move these things around, are completely reversible, right? You can flip the velocity, or you can do inverse of time, and you can go from your final distribution all the way back to the initial condition, because the underlying dynamics is reversible, right? So if you connecting to thermodynamics in completely reversible processes, entropy does not change, right? It's the same logic here. But I think Anupsa's point is that we did not lose any information, right, in propagating this through, right? So going from where you exactly had the particle to the PDF, that's certain loss of information. But that loss of information went from the micro to macro. Once you're in the macro, you're not losing any more information as you are propagating the dynamics through, right? That's why entropy does not. In this particular case, the fine-grained entropy did not change, okay?
But it's because of elasticity.
Yeah, completely reversible. All the dynamics is completely reversible. If the dynamics was not reversible, if the collisions were not elastic, then yes.
So
Then
kind of entropy is a boundary quantity.
exactly, yeah. Okay, let's take a very short break, 3 minutes.